Imagine hosting a party at your house. To get ready, you fill your fridge with various beverages that you purchased at different times. Eventually, all the drinks in the fridge will chill to nearly the same temperature, right? Now, in a similar example, imagine replacing those drinks with atoms. If you could significantly lower the temperature of a group of atoms, they would form a unique state of matter called the Bose-Einstein condensate. You are likely familiar with the four commonly known states of matter: solid, liquid, gas, and plasma. Scientists have extensively researched and studied these states for many years. However, another state of matter is formed when atoms are cooled to temperatures near absolute zero, which is equivalent to 0 Kelvin or negative 273.15 degrees Celsius. During that super chilled phase, the atoms possess minimal energy and exhibit minimal movement. Consequently, they aggregate and become indistinguishable from a physical standpoint, behaving as a single atom. Satyendra Nath Bose, an Indian physicist specializing in theoretical physics, laid the groundwork for this revolutionary theory. He is also credited with discovering the boson, a subatomic particle that now bears his name. Bose sent his ideas to Albert Einstein, a German scientist famed for the special theory of relativity. Einstein then submitted these ideas to Zeitschrift für Physik, a German-language physics journal of the time. To generate the Bose-Einstein condensate, the first step is to obtain a cloud of gas. A typical example is the gas of rubidium atoms. The next step is to use lasers to remove the atom's energy and cool them down. An evaporative cooling method is utilized for further cooling until the atoms are close to absolute zero. At this stage, the atoms assume the same quantum states and operate as a single entity. If you were to measure their location at this point, you would observe a blurred ball rather than individual atoms. The Bose-Einstein condensate was initially predicted in 1924 and 1925, but wasn't created until 1995 by American physicist Eric Cornell and Carl Wieman using rubidium atoms. Wolfgang Ketterle, a German physicist, produced the condensate the same year using sodium atoms. In 2001, these physicists won the Nobel Prize in Physics for achieving Bose-Einstein condensation. Studying particles at near absolute zero temperatures and creating Bose-Einstein condensates has important implications in areas like quantum computing, superconductivity, and scientific research. One example of how researchers use BECs is to gain a better understanding of quantum entanglement. This phenomenon in quantum mechanics explains how particles that are entangled can affect each other's state, regardless of their physical distance. Quantum entanglement is crucial for many technologies, including the fast-emerging field of quantum computing. We have created a separate video about quantum entanglement. You can find the link in the description of this video. Bose-Einstein condensates, BECs, have various practical uses in precision measurement and sensing technologies, which have led to advancements in detecting gravitational waves, creating navigation systems, and improving magnetic resonance imaging, MRI. In addition, BECs have been used to develop atom lasers, which hold great potential for the precise manipulation of atomic matter. This advancement has already aided research in quantum optics and lithography. In 2018, a groundbreaking experiment was conducted on the International Space Station. Rubidium atoms were cooled to nearly 1/millionth of a degree, setting a new record for the coldest experiment ever conducted in space. This experiment also marked the first production of BECs in orbit. So, if the 5 states of matter, solid, liquid, gas, plasma, and BECs, all go to a party, can you guess which one would be the coolest?